Hey folks, for this discussion, we're going to talk about voltage, aka electric potential, around symmetrical conductors, symmetrical spherical conductors. Okay, and I've got two significant examples for you. So the first example is, let's say you have a metal ball. Okay, so it's a conductor, and it can be solid or hollow. It's not going to matter. Okay. And let's say you put a total charge of positive Q on it, and let's say the ball has a radius R. Okay. So first of all, where's all that charge going to go? Well, as we learned previously, all that charge will sit on the very outside of the ball. Okay, so all that Q will go to the very outside of the ball. There won't be any charge inside the ball. What's the voltage at different locations? Well, let me start with electric field. Okay, so we learned in the previous chapter that electric field on the outside of the ball, so anywhere outside the ball, so this would be R bigger than the radius of the ball, it just behaves like a point charge. So it's KQ over R squared. And we also learned that E inside the ball, so that's R inside the ball, is 0. There is no electric field inside that ball of charge. Okay, so if we're looking at voltage, okay, well, voltage outside the ball, so R bigger than the radius, is just going to be KQ over R. It's just going to behave like a point charge. What about the voltage inside the ball, R less than R? Okay, the temptation here is to say 0, and that's not correct. All right. Remembering that voltage is equal to negative, or delta voltage, sorry, is equal to negative integral E dot dr. Okay, well, we know the voltage at the surface of the ball is going to be KQ over big R. It's just this equation with big R plugged in at that point. Now let's say you kept going toward the center of the ball and you integrate it. Well, E is 0. That means now here's the key here, that means your change in voltage is 0. That means your voltage is not changing in the ball. Well, what was the last place that the voltage did change, or the last value of voltage we did know? Well, that was the voltage here at the surface, which was KQ over big R. So it's not going to change. So the voltage everywhere within that ball will be KQ over big R. Okay? If you were to graph these, let's take and this is instructive, it also helps you with your calculus. All right, so we're going to graph E versus R. So there's E versus R. The radius of the ball is a point of interest. And we're going to graph V versus R. So here's voltage versus R. And again, same point of interest, the radius of the ball. Okay. So the electric field, well, it's 0 in the ball. And then it climbs very quickly as you drill through the very thin surface of the ball. And then it's an inverse square out here. Okay, so this would be KQ over little r squared. Okay, now for voltage, okay, when you're outside the ball, the voltage equals KQ over R. The max voltage is KQ over big R. And then since the electric field is 0 in the ball, that means your voltage does not change within the ball. Notice I'm using the word change very carefully here, which means your voltage stays at KQ over big R inside that ball. Okay, so now be careful on a problem like this. So for instance, let's just say I told you the radius of the ball was 4 centimeters. And I ask you, hey, what's the change in voltage between the 7 centimeter mark to the 2 centimeter mark? Okay, well, you can't just use this equation and do KQ over 7 minus KQ over 2. You can't do that because the voltage is a different function if you're outside the ball and inside the ball. What you're looking at is what's the voltage between here, the change in voltage between here and there. So what it would be, it'd be the final voltage, which would be KQ over big R, minus the starting voltage, which would be KQ over little r. Big R in this case would be 4 centimeters. Now, you'd obviously have to convert that to meters, Little r would be 7 centimeters. So that's what you'd plug in for those two values. That would be your change in voltage. So you got to be careful when you're looking at a problem like this one and finding things like change in voltage. You don't have to do all the integration stuff. You can use our shortcuts here. We know on the outside it behaves like a point charge. On the inside, the voltage is constant. The second example I have for you involves concentric spherical shells. So let's say that I have that solid ball, okay, and I'll give it a radius big R, and then I have a shell around it, and let's give it a radius 2R and 3R. Okay, so the parts that are solid here is this is solid metal, okay, and this is solid metal. And I'm going to put the following total charge on these things. This will be a positive 2Q, and this will be a negative 3Q. Okay. Well, first of all, reminder, where does the charge go? Well, all the charge on the inner ball goes to the outside. So there'll be a positive 2Q on the outside of that inner ball. On this outer spherical shell, remember that the electric field inside that metal has to be 0. So this charge on the inner shell has to be negative 2Q to cancel out that positive 2Q. You need the total charge inside that sphere that I just drew, the part of that sphere that I just drew, to be 0. And then if the total charge on this outer shell is negative 3Q and there's negative 2Q on the inner surface, there has to be negative 1Q on the outer surface. Okay, and so what we're going to do is we're going to write voltage at different locations. Okay, so we're going to look at, we're going to start with R outside of the whole thing. So this would be outside of 3R. We'll do at 3R. We'll do between 2R and 3R. We'll do at 2R. We'll look at the voltage between R and 2R. Okay, we'll look at the voltage at R. And finally, we'll look at the voltage at R less than inside the metal ball. So we got a bunch of locations here. Now the good part is you don't actually have to do a whole lot of work here. Remember, if it's a spherical charge, you can basically pretend it's a series of point charges, sort of. So if you're outside this whole thing, it's like one big charge that has a total charge of what? Negative 1Q. So the voltage way out here would be just K times negative Q over R. Okay. At 3R, the voltage would be K times negative Q divided by 3R. Okay, so now we know the voltage here. Now, remember, the voltage within this metal conductor isn't going to change because there's no electric field in there. So the voltage inside of there is going to stay K times negative Q divided by 3R. As a matter of fact, here's where it gets funky. If you're right inside of this thing right there, right just at 2R, right before you start hitting that negative 2Q charge, your voltage is still K times negative Q divided by 3R. So that gets a little confusing, right? It's still 3R here even though you're at 2R. And that's because there's no electric field here, so your voltage doesn't change. Now, what about when you're here, okay, between the two pieces of metal? Well, then you have the following two things you're going to add. You have this voltage plus the voltage created by the 2Q charge, okay? So, or actually, take that back. You have three voltages. I'm sorry. You have the voltage created by the negative 1Q charge. You have the voltage created by the negative 2Q charge. And you have the voltage created by the positive 2Q charge. Okay, so here's how you do that. And I will actually write this down here because we're going to need a little room. So for this one, okay, the voltage is, okay, well, you've got three things. You've got the inner ball, the 2Q ball, and you're outside of that ball, so that's going to act like a point charge. So you got K times positive 2Q over R, okay? Plus, you've got this negative 2q charge here, and it's equidistant. It's a spherical thing, so you do k times negative 2q. Now, where is that at? Well, that's at 2 big R, okay? All right, and then you have the outer charge, which is how far away from the center. Well, that's 3R. So you have k times negative q over 3R, okay? So you're basically adding the effects of this negative 1q, that's here, this negative 2q, that's there, and this positive 2q. And since we're outside of that, that's going to vary. Now, of course, you can combine like terms here if you wanted to. So you'd have k times positive 2q over r, and then you'd have, let's see, this would be a minus. Common denominator here would be 6. You'd have 6 over 6 minus 2 over 6, which would be negative 8 over 6, which would be negative 4/3. So you'd have negative 4kq over 3 big R. Okay, so I'm just combining these two terms and putting it here. Okay, so that would be your voltage in the region between R and 2R. Okay, now how about our voltage at big R? Okay, well, I'll do this down here. Well, all you do is you plug big R in for little r. So you'd have the voltage at R would be K times positive 2Q over big R minus, I'll write this as K times positive 4Q over 3R. And again, these are like terms now if you do your math here. So this left-hand term would become 6Q over 3R. So 6 minus 4 is 2. So you would get 2KQ over 3 big R. So that would be your voltage at R, at the surface of this guy. And the cool part is, what about when you're inside of this ball? What about this last one here, R less than R? Okay, well, there is no electric field inside of here. So your voltage doesn't change. So the voltage at R less than R is this same value. It doesn't change at all, okay? So there's how you find voltage for concentric conductors, okay? Now, one last little thing I'll mention on this about conductors and voltages. You will encounter problems like this. Let's say you have two equal size metallic spheres, and let's say you put a total charge of 20 nanocoulombs on the left sphere, and then you connect these with a conducting wire. How much charge ends up on each sphere? Well, if they're equal sizes, then it will be negative 10, or sorry, 10 and 10 nanocoulombs, okay? So that's an easy one, right? But what if they're different radii? What if you have this, and let's say you put your 20 nanocoulombs on there, and then you have a small one, okay, and you connect them with a conducting wire or something. How will the charge distribute now? Okay, well, here's the deal. The total charge, we'll call this A and we'll call this B. We know the charge on A plus the charge on B is going to have to be 20 nanocoulombs, right? So some of this charge will go over to the right-hand sphere. The question is how much? It's not going to be 10 this time. It's going to be something different. So what else is going to have to be the same for the two spheres? Well, it turns out that the voltage of the two spheres will have to be the same when electrostatic equilibrium is achieved. So what will happen is the charge will move until the voltage of A is equal to the voltage of B. Now remember, voltage for a conducting charge when you're at the surface of it or anywhere in it is K. So this would be KQA over RA would have to be K times Q on B over RB. Those voltages would have to be the same. And remember, QA plus QB is 20 nanocoulombs. So you have two equations, two unknowns. You got QA and QB, and you have two equations to try to solve for QA and QB. So, all right, so that is a brief summary of voltages due to conducting charges. So if they're spherical charges, you treat them like point charges. If you're outside of them, if you're inside of them, the voltage does not change because the electric field is 0. Hope that video was helpful, and thank you very much.